hello everyone. So before we get started, just to know of your background. So you are mostly from electrical or physics. So if you can just type in the chat box, or you can just unmute and say all if you want. Physics, okay. I got 2 physics. Okay, a lot of physics. I see mostly physics till now. Okay, so this is the 3rd day of the course. So I see actually all physics. Yeah, okay, that's good. So this is the 3rd day of the course, and you have been looking at I think quantum mechanics, then solid state physics. So in this lecture, we take all that learning, all that physics, and try to apply it to devices which can be used for some useful applications. And we, of course, look at the physics background of the different aspects of what goes in the devices. So at any point during the talk, just stop me if you have any questions and ask it. Okay, let's keep this very interactive. So, okay, so now, what are useful devices? Okay, so you have all know about PN junctions, transistors. So essentially, as electrical engineers, what we want to use is devices with some interesting IV characteristics. That's what we want to make, so that they can be applied for different applications. For example, this is something you are very familiar with. This is just a resistor which has a nice linear IV. Then we have devices that have rectifying characteristics, that if you apply voltage in one direction, they conduct very nicely, but in the other direction, they don't conduct or they block the voltage. And these are used for rectifier applications, AC to DC conversion, and there are many other applications. If you shine light on a device like this, its IV characteristics become something like this. So this is a solar cell. Now, in this 4th quadrant, you can essentially have the product of V and I negative. Essentially, this device can act as a power source now, rather than consuming power. And similarly, there are devices that break down, which are like diodes, but they break down at certain voltages, which can be used at voltage references. Or there are devices which have characteristics like this, which are 3-terminal devices, in which we can control the current between 2 terminals by applying voltage or current on the 3rd terminal. So this can be either a bipolar junction transistor or a MOSFET. And these devices then can be used as switches, which either allow the current to flow or not to flow. And this is what is used in all our laptops, mobile phones, essentially all computers. Okay, that is the basis of logic, a switch. Then we can also use this as an amplifier, by which we can apply a small input signal and amplify it if you have a device which has such a device characteristics. So, and similarly, there are devices that show behaviors like this. Essentially, they have a memory built into them. They are resistors, but they have a memory built into them. They are called memristors. So there are all these kind of interesting IV characteristics which enable all these different applications. So,
Dr. Amit?
Yeah.
Sorry to disturb, because you have said a very interesting thing about the solar cell. You told just, I want to request you to repeat it again, please.
So see, what I was saying is, so if you look at a resistor, the IV characteristics is there in the 1st quadrant and the 3rd quadrant. So V times I across it is positive. So it always consumes power. On the other hand, you look at a battery. Okay, you have a battery and apply it to a resistor. the V times I product across it would be negative, which tells us that it's a power source.
Right. Thank you, Dr.
Yeah. So I have established that, see, we are interested in all kinds of different interesting IV characteristics so that we can enable different applications. So how do we essentially understand these IV characteristics? How do we design them? How do we engineer them? So this talk essentially will be in the background of the course, but taking you from what you have learned, but towards device side. So let's look at these IV characteristics. So IV has two parts. So there is current and then there is voltage. So you know what is current? You suppose you have a conductor and you have some carriers there. And you have some imaginary cross section across which these carriers are crossing. And we define the current density as the number of carriers per unit area per unit time that cross this cross section. And this current density essentially can be written as the charge of the electron times the density of the electrons multiplied by their velocity. So this is the base expression which is always valid, okay, irrespective of how do you calculate the velocity or how do you get the n. So this will become more clear as I come later on. We discuss different transport theories in which we calculate the V in quite different ways. So first thing, when we are looking at current, you can see is we have to know how many mobile carriers do I have. I need to know n in any material in which I want to calculate the current. Now this question actually is not so trivial. The reason being, for example, in silicon, okay, silicon has an atomic number of 14 and the configuration is 1s2, so it has 14 electrons. But are all 14 electrons, when you make a silicon semiconductor or solid, are all those 14 electrons contributing to conductivity? They don't, right? To answer all those questions, you need quantum mechanics and the concepts of band structures, which is what you have been looking at in past 2 days. So how do we calculate mobile carriers? That is the first thing we have to worry about. Then second thing we have to worry about is what is the velocity with which these carriers move, or essentially the transport aspect. And this is also quite involved and we'll come back and look at it in great depth. And to know all these, essentially what I was saying, you need to know kind of quantum mechanics background is needed to answer these questions. The concept of band structure, density of states, occupation functions such as the Fermi-Dirac distribution, which you have looked at. And then to answer the questions about velocity, then we have to look at materials where electrons can move without scattering, with scattering, what all things happen. So that is what we will look at during the course of the talk. Now let's look at the second part. So we are looking at current voltage characteristics. So second aspect is the voltage. So what does voltage do? So to give you an idea of what happens, so just quick review of the electrostatics you are aware of. Okay, so you know in Coulomb's law, if you have two charges, there is a force between them as given by this equation, and essentially you can define the potential energy of this two charge system. So if you take and plot the potential energy of one charge as a function of position, suppose this is a positive charge, the potential energy profile goes as plus Q by R. So essentially this is how the potential. Now it is very intuitive once you start looking at this picture that if I bring a positive charge close by, so this is the potential energy for two positive charges. So if I bring a positive charge close by, it will try to go downhill. So we have this intuition about gravity, right? Because we feel that quite often in our environment, that if there is a mountain or a hill, I leave a ball, it will automatically go down. Similarly, if you bring a positive charge here, it will automatically go away because there is a repulsive force between them. Similarly, if I bring a negative charge, my potential energy profile is something like this. So if I bring a negative charge, leave it here, it will try to come as close as possible to the positive charge. So what potentials are, as you apply potentials across your devices, they generate potential energy landscapes, which either make the flow of carriers easier or make, like you are aware, you are driving a car. Okay, if you have a mountain, you have to spend a lot of energy to overcome it. On the other hand, if you are going down the mountain, you can go very easily. So very similar ideas are there, but just that now by applying voltage, we are creating the energy landscapes for electrons. Now, this is for a single charge. When we are dealing with solids, the relevant equation is the Gauss law, the Maxwell's first equation, essentially, which tells us that the divergence of the electric field is the net charge density inside the material divided by the vacuum permittivity. And then we can go from the electric field to the potential by integration, and we can find out what is my potential energy by multiplying this. So we always draw these energy landscapes. These are called as band diagrams. So I'll come to this topic later on also. So essentially, there are three aspects which we need to understand if we want to understand semiconductor devices and the IV characteristics and their IV characteristics. So essentially, one is what is their mobile carrier concentration? What is the electrostatics, that how the voltage gets distributed, what are the potential energy landscapes? And then third point is the transport aspect, that what is the velocity of the carriers. So let's quickly look through them one by one. The first of these is the mobile carrier concentration. This you have already looked at, I think, a little bit in last 2 days. So I will go a little bit quick. If you want any point clarified, just stop me there. So you are aware of, so this point I already told you that we start with an atom. Now, each atom has a bunch of electrons. For example, silicon has 14 electrons around its nucleus. And there are discrete energy levels. Okay, we know we specify them with principal quantum number, azimuthal quantum number, magnetic quantum number. So all these discrete energy states are there, and the electrons are filled as 1s2, 2s2, 2p6, 3s2, 3p2, something like that. Now, when you bring these atoms together and form crystals, essentially, now to describe the behavior of electrons inside these solids, we use the concept called as band structure, which are essentially the allowed energy states for the electrons moving, having a certain K inside the crystal. Okay, so this is the starting point. I'll assume, so I'll not go into how these are calculated, because I think that is something you looked in great detail in the talks on density functional theory and other things. Now, once you have the band structure, you can answer a lot of questions about this material, whether it will be a good conductor, whether it will be a bad conductor, whether it will be a semiconductor. So all these questions essentially are decided by how electrons are filled in these bands. So we have to know of another concept, which is the distribution of these electrons, which under equilibrium conditions is given by Fermi-Dirac distribution for electrons, because electrons are fermions, spin half particles. So essentially this function says that if the energy is much larger than the chemical potential, or what's known as Fermi level, much larger than that, that state will have a very low probability of occupation. On the other hand, if the energy is below the Fermi level, there will be a very high probability of occupation. So there are materials in which once you do the filling of the electrons in the bands, the Fermi level will come between a band. Okay, somewhere in between where the density of states is non-zero. And these materials behave as metals. Example, aluminum, copper, gold, they are all very good metals. Then there are materials in which the Fermi level lies somewhere in the band structure where the density of states is zero. So since the density of states is zero, these materials behave either as semiconductors or insulators. Now, in these materials, okay, so we are now interested in these semiconductors. So in these materials, so this is a band structure of silicon. Essentially, all these bottom bands are filled. This is the topmost band that is filled. This is known as valence band. This is the lowest band that is empty. This is called as the conduction band. And the energy difference between the minima of the conduction band and the maxima of the valence band is the band gap, which is about 1.1 electron volt for the case of silicon. Now, essentially, our Fermi level for silicon lies somewhere in this band gap. Now, at any finite temperature, the electrons from the valence band can get thermally excited to the conduction band, so that you have some free carriers in the conduction band and some empty states, or what is also known as holes, inside the valence band. Now, in transport, we know that any full band which is completely full or completely empty cannot contribute to current. Only partially filled bands or partially empty bands can contribute to current. So, as far as semiconductor devices are concerned and current calculations are concerned, we are only concerned with the part of band structures where there are filled states, partially filled states, or partially empty states. So essentially that means lower part of the conduction band and top part of the valence band. So we just want to describe these parts in an accurate way. And for that, we often make an parabolic approximation. We fit a parabola to these minimas and maximas and get a fitting parameter, what is known as the effective mass. So the dispersion relation or the shape of this band structure around a minima or a maxima can be written as E minus EC for conduction band equals to h square k square by 2m star. Now this is the dispersion for a free electron. Right, free electron has only kinetic energy, no potential energy. Kinetic energy is half mv square, which you can write as m square v square by 2m naught or p square by 2. So it is exactly same as this equation, okay, because p is equal to h bar k from the de Broglie relation. So what this tells is my electron behaves like a free electron. Okay, even though it's inside a semiconductor, it behaves as a free electron. So for all practical purposes, we can treat it as a free electron having a mass, which is this effective mass. Okay, so now we know these things. We are only concerned with part of the conduction band and the top part of the valence band. At any finite temperature, we want to find out how many carriers do I have. So remember, the first thing we are interested in is how many carriers do I have so that I can make a current calculation. So how do I calculate the number of electrons? The number of electrons, essentially, you can count how many states are there multiplied by what is the probability of occupation of those states. So how many states are there is given by the density of states. I think a concept which was covered in one of the earlier lectures. So this is the density of states function multiplied by the Fermi-Dirac function. And if your Fermi level is within the band gap, you can simplify this integral and get this formula, that where the electron concentration is something known as the effective density of states, e to the power minus conduction band minimum minus the Fermi level by kBT. Similarly, you can find out the whole concentration, or how many empty states do you have in the valence band, which is also how many states are there and what is the probability of these states not being filled. We are looking at empty states. So this is the density of states in the valence band multiplied by 1 minus the Fermi-Dirac function. So Fermi-Dirac tells us the probability of occupation. So 1 minus that tells us the probability of being empty. Again, if your Fermi level is somewhere in the band gap, one can simplify this and write it the whole concentration as a function of the Fermi level. So these you might be familiar with. And as you change, so if you are working with 3D materials, then there are 2D materials such as MOS2, there are 1D materials like nanowires. So all that happens, all this theory is still valid. The only thing that changes when you are calculating carrier concentrations is the density of states function. So the density of states for the case of the 3D materials varies as square root of E. Okay, this is what is there in silicon, bulk silicon, gallium arsenide, and all these cases. Then there are two-dimensional cases. For example, MOS2 or in a MOSFET, we create an inversion layer, which is also two-dimensional, or a high electron mobility transistor, where also there are two-dimensional electron gases. In all of those cases, the density of states is a constant, it's m star by pi h bar square. Then we can have nanowires in which the density of states actually goes as 1 by square root of phi. Okay, so now we have all this. Now I try to calculate the carrier concentration. I have expressed the electrons as a function of Fermi level, holes as a function of Fermi level, and I'm taking a pure semiconductor right now, intrinsic semiconductor. So we know that the electrons that are there in conduction band have come from the valence band. So the number of electrons in the conduction band have to be the number of empty, have to equal to the number of empty states inside the valence band. Okay, so this is known as a charge neutrality principle. So essentially Ni is equal to pi. So once you solve this, there is only one unknown, which is the Fermi level. So you can solve this and you get Fermi level expression, which is something like this. Essentially, Fermi level lies somewhere within the center or close to the center of the band gap, with the slight asymmetry because of the different effective masses of the conduction and valence bands. Once you know this, you can put this back in any of these expressions and find out the number of carriers. And this is the expression one gets. Essentially, larger is the band gap, smaller is the intrinsic carrier concentration. So let's put these numbers. So silicon has a band gap of about 1.1 electron volt. At room temperature, if you put everything, the number you get is silicon has at room temperature for intrinsic silicon 1.5 into 10 to the power 10 electrons per centimeter cube of electrons and same number of holes. Now compare this to metals, which have an electron concentration of the order of Avogadro number, right? 10 power 22 or 10 power 23 electrons per centimeter cube. And they have very good conductivity. Compared to that, 10 power 10 is a very small number. Okay, 12, 13 orders small. So this material will not be a good conductor. So this is not what we want. We want more carriers. So how do we get that? So we get that by a process known as substitutional doping. Essentially what we do, we take, for example, in silicon, silicon has 4 electrons in its valence shell. So we replace silicon with an atom in group 5, which has 5 electrons in its valence shell. For example, arsenic. So 4 of these electrons are used to form the sp3 bonds. and that the fifth electron is very loosely bound to arsenic. Okay, so essentially this fifth electron, if you give a small energy, it becomes free. Equivalent terms, if you want to understand it, what happens, this extra electron makes an extra energy level in the bands just below the conduction band. This is called as the donor level. And by giving very small thermal energy, these electrons can ionize and become free and move in the conduction band. So essentially now you can control how many carriers you have by controlling the number of arsenic or any group 5 impurity you are putting in the material. Similarly, one can dope the material p-type by creating more holes by putting an element from group 3 into silicon, which will create an energy level just above the valence band. Now this element, for example, boron, has only 3 electrons in the valence shell. So 1 electron is less. So it can accept 1 electron from the valence band and create a vacancy in the valence band, which can act as a hole or a current carrier. So this is known as substitutional doping. Now, you have to be a little bit careful if you are like from the fabrication side of things, that these atoms have to substitute silicon. If they are just present in the lattice but not substituting silicon, they will not act as a donor. So it's very important that they substitute the element and form bonds. Okay, now once you have done this, now you take this doped semiconductor, go to a lab and do a Hall effect measurement. Now Hall effect is in which we do 2 measurements. We measure the resistance of a sample to calculate the resistivity. Then we apply a magnetic field and find out what is known as a Hall effect. And from that, we can find out the concentration and also what's known as the mobility of the carriers. If you do that and plot the carrier concentration in the material as a function of temperature, so here it's inverse temperature. So this is higher temperature, this is lower temperature. So essentially, if you go to very low temperatures, so you know there is this activation energy of carriers needed. There will not be, as you go to low temperature, there is not enough thermal energy. So essentially, these carriers are not able to ionize. They will stay here. So they will not create mobile carriers. So the mobile carrier concentration decreases. You increase temperature, all of the dopants you have put, they will become ionized and they will give you a nice constant carrier concentration. So this is 10 power 15 donors have been put in and you get 10 power 15 electrons per centimeter cube. And if you keep on increasing the temperature, ultimately the electrons that get thermally excited from the valence band, they become dominant compared to the electrons that are coming from the donor atoms, and you have the intrinsic behavior. This happens at very, very high temperatures though. Okay. So essentially, you can now control this carrier concentration by applying by putting in different amount of impurities inside your semiconductor. So this is one of the reasons we have to maintain extreme purities while doing fabrication of devices, and the materials we use in the fabrication have to be extremely pure, because a very, very small impurity like a parts per million can change the conductivity of the materials very, very significantly. Okay, so remember, this is 10 power 15. Avogadro number is 10 power 22, 23. So this is only 10 to 100 parts a billion. Okay, so very, very small amount of impurity that has been added. Now, how do you actually find out whether the donor atom I have put in, if I know its activation energy, whether it will be in extrinsic region, ionization region, or intrinsic region at any temperature? Again, you go back to the charge neutrality principle. You know that the total net charge in a uniform semiconductor has to be 0. So the positive charge has to balance the negative charge. Positive charge is the whole concentration plus the ionized donors, and the negative charge is the electrons and the negatively charged acceptors. Now, P and N we already know as a function of Fermi level. Nd plus can also be expressed as a function of Fermi level as such. Nd plus is the number of ionized donors. Nd is the total number of donor atoms we have put in. And Gd is just a degeneracy factor, which is 2. This is the Fermi level and this is the donor energy level. So again, the only unknown in this is EF, similarly for Na-. So this equation has only one unknown, which is EF. So you solve for that numerically. Once you know that, you can substitute and find these terms individually and get a curve something like this. So this is the power of semiconductors. So as I was saying earlier, resistivity, see, of metals, which is one type of materials, is of the order of 10 to the minus 6 ohm centimeter. On the other hand, there are very good insulators like silicon oxide, which have a resistivity of 10 to the plus 14 ohm centimeter. So about 20 orders difference. Now, the power of semiconductors is by doping them with these impurities, we can change their resistivities or conductivities over many orders so that we can tune them to the application we need. For example, here it is shown that the silicon doping density can be varied all the way from 10 to the power 21 to somewhere around 10 to the power 12 or so. Okay, just by changing the doping concentrations, and similarly, you can change its resistivity also. So some terms to be aware of. So we use this very often in devices. We will say N-type, P-type, but sometimes we will say N minus, P minus, or N plus, P plus. So this is just to talk about the extent of dopings. So earlier we were talking about the effective density of state. If you remember, that expression came. Now a typical order of effective density of states is about 10 to the power 19 per centimeter cube or so. So any doping which is much less than this or slightly less than this will be called NP. If you go much lower than that, it will be called N minus, P minus. On the other hand, if you go much higher than this, we will call it N plus, P plus. Okay, so before I move on, any questions in this part? I hear some voice, but it's not coming clearly.
Good afternoon, sir. Am I audible now?
Oh, actually, your voice is coming very low. If you can speak a little louder.
Sir, I can write the question in the chat box. That will be beneficial.
Actually, I can hear you now. So try it once. If it doesn't work, then you can type it. Yeah. Hello. Yeah, I cannot hear you now. Perhaps you can just type it then. Yeah.
Hello, sir.
Yeah.
Sir, I have one query. So, can you tell me what are the best simulators, device modeling simulators?
So device simulators, you mean more like TCAD?
Yes, sir. Yes, sir.
So it depends on what you want to do. So see, there are some commercial simulators such as Taurus, Silvaco.
Okay.
Then there are some other ones. If you want to include quantum effects, there is what's known as Next Nano, which is a reasonably good simulator. So there are quite a few like this. Yeah.
So all are licensed only?
Next Nano, so Centaurus and Silvaco are licensed. Next Nano is licensed, but it's developed by a university. So for people, if you drop them an email, I think they are much lower priced compared to Centaurus and Silvaco.
Okay.
Yeah.
Okay, sir. Thank you.
Okay.
Hello, Namaskar, sir.
Yeah, namaskar.
Yes, sir. So actually, I just want to ask that both band structure and density of states, both plots are used to determine the value of band gap. Then, so how dose and band structure basically different from each other?
Band structure and what is different from each other?
Density of states, dose diagram.
So see, band structures, let me go to maybe a band structure. So see, this is the band structure.
Yes, sir.
Okay, now what you are seeing actually in each of these bands, there are many states which are close to each other. Just like if you remember, for in atoms, you have discrete energies of electrons, right?
Yes, sir.
Similarly, on a band structure also there are discrete energies, but they are very close to each other. So what density of states tells you is what is the density of these closely spaced states at any point. So when you draw D of E, that tells you that how the density of states rises. For example, in the band gap, there is zero density of states. There is no states there. As you go in the conduction band, your density of states will start to rise. Similarly, in the valence band. So density of states is telling you the density of how many states are present in the band structure.
Okay, sir. And basically, these symmetry points that L, gamma, delta, X, we do have that same kind of any repetitive presentation for FCC, BCC, and other structures. So what if I want to make a structure which is neither BCC, neither FCC, orthorhombic, maybe kind of mid kind of structure? For that, what kind of symmetry points do I need to take?
Oh, actually, see, these are very well established. So, so this was done in 1800s. That how many types of symmetries are possible. So, from mathematics, people figured out that what are all possible symmetry types that are there, and that's how they came to what are known as 14 Bravais lattices.
Yes, sir.
Right. So now, once you have the Bravais lattices, the reciprocal space for them is also fixed. All you have to do is do the Fourier transform of them. So once you do that, because they are fixed, so all these LK, all these things have been defined. They are, it's convention, what you call them.
Okay, so what if I just want to make a heterostructure of two different compounds? For example, one is HBN and the other one is graphene. And if I want to make a heterostructure, and after that heterostructure, what symmetry points do I need to take for that?
Okay, so see, you have two materials whose heterostructure you are making. So I'll talk about heterostructures and when I talk about band diagrams. Okay, essentially, sir, HBN will have its band structure and graphene or whatever other material will have its own band structure.
Yes, sir.
Now, as you go from one material to the other, the conduction band changes. So this spatial variation of conduction band is what is known as band diagram.
Yes, sir.
I'll come to that. So that is what you worry about. There you don't worry about band structure, but you worry about band diagrams when you are spatially changing things.
Exactly. First, we need to determine the phonon, and after phonon, we can know the system stability. After that, only we can go for band diagrams.
See, I'm not very sure what you mean. See, system stability, suppose you are doing density functional theory calculation. Okay, yes, you are designing kind of a new material. Then you do the stability analysis of a given structure. You minimize the energy. Then once you have minimized the energy, you find the band structure. Now, once you have the band structure, you can know about its electronic properties, magnetic properties, all those kind of things.
Yes, sir.
Now, band diagram is something when you are now making a device out of that material.
Okay.
Where there is a spatial variation versus position. Right now, in a band structure, you are varying as a function of K of the electron.
Yes, sir.
In a band diagram, we are looking at energy versus position.
K diagram, yes, sir.
This is EK, that is E versus X.
E versus X. Okay.
Okay, so when you are making these heterostructures, then you usually look at those E versus X curves.
Okay.
I'll come to that. So I'll right after this, that is the topic or discussion.
Okay. Thank you so much, sir. Very well explained.
Yeah, thanks. So
Good afternoon, sir. Excuse me, sir.
Yeah, sure.
Sir, actually, what is the difference between the concentration of mobility and mobilization force of both the electrons and holes?
Say that one more time. Concentration of mobility.
Mobility concentration and mobilization force.
Mobilization force.
Yes.
I'm not too sure. I have not heard this term. Yeah. Do you mean, so see, when there is an electric field, the electron is a charged particle. So that electric field forces it and the electron starts to move because of that.
Yes.
So what do you mean by mobilization force? Yeah, I have not heard that term before. Yeah.
Sir, why the valence band is lower than conduction band in both the electrons and holes in any semiconductor?
Can you say that little bit slowly?
Sir, why the valence band is lower than the conduction band?
See, that is how it is defined. It's just a naming convention. We said that whatever is the topmost filled band, so you fill from bottom, right? Once you fill electron, first you fill the lowest energy, the next energy, then the next energy. Thermodynamically, that's how you want to keep the energy lowest. So
Only
the highest.
The energy level.
Sorry?
Sir, only the reference of energy level.
Energy level. Right. Like you have 1s2, 2s2 levels, you start filling from the lowest energy level. Okay. So similarly, you fill these bands. The highest band that is filled, we decided to call it valence band. Okay, that is just a convention. There's nothing special about it. We decided to call it valence band. And the lowest band, which is empty, we said we will call it conduction band. That's it. That's the convention.
Yes, sir. Thank you, sir.
Sir, will you be also explaining the concept of intercalation?
Intercalation, not so much, yeah.
Okay, sir.
Yeah. So see, intercalation is a process in which, see, for batteries and a lot of these applications, it's important. So that is more changing the kind of band structure of the material by putting in very high number of other atoms in there, by changing the structure or something. So I'll not go into that, yeah.
Sir, any physical meaning of this which is used on k-axis like L, lambda, R and X, these terms?
These things?
Yes, sir.
These are high symmetry points. So, okay, so you know, cube has a very high symmetry.
Yes, sir.
Right. So when you take a cube, so this is for silicon. So you start from a silicon crystal structure, which has quite a high symmetry. Then you go to its reciprocal space, which also is very symmetrical. So these are high symmetry points of the first Brillouin zone of the silicon reciprocal lattice. So okay, gamma is for k equal to 0. So these are kind of comes from conventions. So gamma is for k equal to 0. Then you go along x direction. That is what x is. So to explain that, we'll need actually a full lecture in its own. But if you are interested, you can look at actually any of the solid state books. Kittel has good explanations on this, and certainly Marmen's book.
Okay, sir. Fine, sir. Thank you, sir.
Yeah.
Yeah. Good afternoon, sir.
Good afternoon.
Yeah. Sir, I have a question that why do we say that electron has more mobility than holes?
See, that is need not always be the case, but usually it is the case. The reason being, the effective mass of the electrons, this curvature, is usually smaller compared to the valence band curvature. And because of that, the velocity, so the velocity of the electron or the mobility later on we will see is given as electronic charge times the scattering time tau divided by the effective mass. So because electrons usually have a lower effective mass compared to holes, mobility is usually larger.
Okay, thank you, sir.
Mhm. Yeah, I think Dr. Anshuman, I think this was your question also. I hope it got answered. Yeah. Okay. Any other questions before we move on? All right, so let's keep moving then.
Yeah, I don't think any other questions is there. So,
Okay, all right.
Yeah.
So essentially, we have looked at the first part of what for the current voltage characteristics calculation, that how do we calculate these carrier concentration. Now we come to the second part, that we are applying this voltage and that creates a certain potential energy landscape. So this is what's known as a band diagram. So these are actually the heart of semiconductor devices, and that importance has been emphasized by Professor Herb Kromer from Santa Barbara, who is a Nobel laureate from 2001, that he has these Kromer's lemma of on band diagrams, that if in discussing a semiconductor problem, you cannot draw an energy band diagram. Okay, this is not band structure, this is band diagram. This shows that you don't know what you're talking about. And the other thing is, if you can draw one, but you don't, then your audience won't know what you're talking about. So these are actually very, very intuitive pictures to understand how the device behaves. So I'll give a device example later on in this part, which will kind of give you an intuition that how useful they are. So how do you come to a band diagram? How do you make one? So what are band diagrams? So in the band structure, you know where is the conduction band, where is the valence band. That is E versus K. Now a band diagram is how does my conduction band minima and conduction and valence band maxima vary as a function of position in my device. Position. Okay. How do we get that? So essentially, we start from our Gauss law or Poisson equation. So this is del 2V, which is minus divergence E. That is equal to rho by epsilon. Okay, what is the net charge in the material? In semiconductor, the charge can come from electrons, holes, donor ions, acceptor ions. Once you know this, so you have to know this as a function of position. Usually in a device, we change the dopings and concentrations. We vary them as a function of position, right? For when we make a PN junction, we dope one side P, other side N. When we make a MOSFET, we say for a NMOS, we have a N plus P, N plus kind of a structure. Similarly, for a BJT, we have NPN, PNP. So in all devices, we vary the doping, and as a result, the potential gets varied in an interesting way in the device. So once you have this Gauss law and you know what doping profiles you have taken, plus of course the electron concentration, if you can find potential, what is the potential energy? So band diagrams are drawn for electrons. So you take the potential, you multiply with the charge of the electron, and you have your potential energy. Minus E times the potential is the conduction band minima variation as a function of position. And the valence band will of course be different from conduction band by the band gap. That's it. Once you know this, you can also find the field. Field you know is minus dV by dx. You can substitute here. So field is 1 by E times dEc by dx. So essentially, the slope of these band diagrams tell you what is the local electric field. That's it. Okay, nothing more than this. So before we go further on this, let me give you some examples Okay, some kind of blocks which are very useful in making band diagrams in semiconductors. So suppose you have a sheet charge. Okay, such sheet charges are generated very often as interface charges, or in gallium nitride, there are polarization charges, there is an inversion layer. So these kind of charges very often come in devices. So suppose you have a positive sheet charge, okay, so this is my charge. You can do integration of this charge in using Gauss law and find out the electric field. And you know what is the electric field? It is sigma by 2 epsilon s going away on both sides. Okay, I'm assuming an infinite sheet charge for now. So essentially I have a constant electric field, positive in the positive direction, and a constant negative electric field in the negative direction. I do one more integration of this field as a function of position and I get potential. Once I have the potential, I can multiply that with minus E and I get the conduction band. Okay. So actually, I'm not too sure whether you can see the lower part, because in my screen, this zoom bar is coming. Are you?
I can see it.
You are able to see.
Okay, yeah,
so then it's only in my.
Yeah.
So that is fine then. So you can see that the conduction band varies like this. So it is very intuitive from this potential energy picture that if you leave an electron in this, it will try to come to the minimum. And this is what happens. If you take an electron and leave in the field of a positive sheet charge, it will get attracted towards it. So this kind of a behavior of charge carriers becomes very obvious or intuitive once you draw the band diagram. Similarly, you can do for the negative sheet charge. Essentially, you will get a upward facing peak kind of looking thing. So that if you leave an electron, it will try to go away from it. So essentially, we go between charge to field to bands. So these are some exercises which you can try out. These are some typical charge densities which are found in semiconductor devices. Okay. One is, of course, a neutral region in which there is no net charge density. In that case, there is no net field, and the potential energy is also constant. So essentially, your conduction band minima and valence band maxima remain constant as a function of position. If you have a positive slab charge, okay, in that case, you can integrate it once, you will get a field which looks something like this. Okay, sigma by 2 epsilon minus sigma by 2 epsilon away from it. And within it, it will be linearly varying because it's constant. When you integrate that with respect to position, you will get some c times x, a linearly varying function, which is this. When you integrate this one more time, then in the region where the field was constant, now you have a linearly varying conduction band, and the place where you had a linearly varying field, you will have a parabolically varying conduction band. Okay. So again, very clear, if you leave an electron in this field, it will try to come to this bottom or come closer to this positive slab charge. Similarly, for a negative slab charge, for a positive sheet charge, for a negative sheet charge, and for a dipole. Okay, so once you have a dipole, you can essentially create a barrier for the electrons. Okay, so this is a barrier. This is what we do in case of a PN junction, as I'll show later on. If you want to remember this, some of these, see, one way we remember this is, so positive, like positive energy. So you can remember a smiley face, which is positive. So this is like a smiley face. While there is a negative charge, so you make a frowny face if you are negative. So this is a frowny face. So once you know of these basic things, so essentially what we have to do in whatever device we are interested in, find out the charge density, integrate it once, find out the field, integrate it one more, find out the potential, multiply with minus E, and have your conduction. And then valence band you can get by subtracting the band gap. Now, where do interesting device behaviors come? Okay, so this is another saying by Professor Herb Kromer, interface is the device. Whenever you make interface between same material or two different materials which have different properties, some interesting device behavior comes there. Okay. What can be the difference? It can be just different doping. For example, one side P, other side N. And because of that, you can actually create barriers in the material, which can lead to rectifying IV characteristic. Okay. It can be a heterostructure between two different materials. You can have conduction band, valence band offset. So these are used for making high electron mobility transistors. Then it can be two different materials like as metal and semiconductors. So you get Schottky diodes, or like what the lady earlier was mentioning, say HBN, graphene, or whatever two materials. So when you put them next to each other, what happens is charge transfer can happen between the two. And because of that, barriers get created. These barriers are naturally present when you have two different materials. And these barriers, think of them again like you are changing the potential energy landscape. Remember, electrons are living in conduction band in these energies. So if I have an electron here, it goes here, it sees this barrier. So think very, very intuitively, right? Like there is a mountain, there is a barrier on the road. Similar to that. So an electron sees this barrier inside the device. And similarly, when you use these two materials, say a PN junction, you create these barriers. And that is what leads to rectifying characteristics. Okay. So some of the energies we have to be aware of when we are drawing the band diagrams is if you are working with a metal. So suppose you are making an ohmic contact or a Schottky contact. For metals, the thing you need to know is what's known as a work function. Work function is the energy needed to take an electron from the Fermi level and make it free. Okay, free with zero kinetic energy. So that is kind of a reference energy that is known as vacuum level. So you take an electron and make it free. On the other hand, when we are dealing with semiconductors, there are a number of energies we need to be aware of. One is, what is the energy between the conduction band and the vacuum level? This is known as electron affinity. Then what is the energy between the vacuum level and the valence band? This is known as ionization energy. So ionization energy and electron affinity difference is the band gap. And then what is the work function? Work function is again the difference between the Fermi level and the vacuum level. Now remember that for a semiconductor, just by doping, we can tune its Fermi level all the way from valence band to the conduction band. Okay, even within the valence band to within the conduction band, just by doping. So what happens? So once you know these things for all the different components of your device, when you bring them together, what happens? Fermi level is something like a water level. So if you have two buckets in which one is filled with water till the top, while other is filled with water only at the bottom, you connect them with a pipe. Okay, what will happen? The water will flow from the bucket which has a higher level to the bucket which has lower level till the levels equilibrate. So Fermi level is a very similar concept for electrons. Essentially, when you bring together materials which have different Fermi level, electrons will flow from the material which has higher Fermi level to the material which has lower Fermi level till the Fermi level becomes equal throughout the device. Okay, this is the condition of equilibrium. Now, a very interesting thing happens when you do this. One thing, so initially, see, suppose you have doped this semiconductor. So the number of donor ions will be equal to the number of electrons. So the material will be neutral. Now, when you bring two materials together and one say this loses electrons to the other material, this material will no longer be neutral. Now there will be net positive charge in this material. And that net positive charge is what leads to band bending or shaping the potential energy landscape. So let me take an example. So this is, let's say I have, say, silicon or any semiconductor for that matter, same material. On one side, I dope it p-type. On other side, I dope it n-type. When I dope it p-type, the Fermi level actually is very close to the valence band. What that means is there are quite a few empty states inside the valence band or high concentration of holes, and very, very few filled occupied states in the conduction band or very few electrons. Now, on the other side, I dope it n-type, where the Fermi level would be closer to the conduction band. I bring these two in contact. Now the Fermi level here is higher, here it's lower. Right now, both these materials are neutral. Now, as I bring them in contact, electrons will get transferred from this side to this side. Because of that, this side will actually get positively charged, while this side gains electrons. These electrons will recombine with the holes, and there will be net positive charge on this side. Negative charge, because these electrons are coming from here to here. And of course, this positive charge will be equal to this negative charge because you are just rearranging the charges. That's it. Now, when you do this, what happens is you generate a slab charge on this side, slab positive charge. So what are the charge components on n-type semiconductor? You can have either donor ions, Nd+, which are positively charged. You can have electrons, N, and you can have holes, but holes will be very few. So you don't need to worry about holes. So initially, Nd+ and N were balancing each other so that the net charge in this region was 0. Now, as soon as these electrons go to the p side, Nd+ becomes dominant. Nd+ cannot change, right? Donor ions are fixed, they are bonded. Only electrons are moving. So you have a fixed Nd charge left out in this region. Okay, you create what's known as a depletion region, which has a fixed charge of Nd+. That's a slab charge. Similarly, these electrons recombine with these holes, creating a depletion region here, which is negative, which is Na-. Because on p side, you have charges which are either Na- or p, only two charge components. Holes you are removing by recombining with these electrons. So you have only Na- charge left out, which is also slab charge. For slab charge, you know how the conduction band varies. For positive, there is a smiley parabola. For negative, there is a downward frowny parabola. So essentially, this is how the band looks like. And the valence band you can draw because the difference between the two is the band gap. And essentially, we have the Fermi level is flat in the equilibrium. So if you go one side, you can see you have large carrier concentration of electrons. Okay, Fermi level closer to conduction band. As you go in this region, the Fermi level starts going away. That means electron concentration is reducing. So this is the depletion region on the N side. Then you come to the other side. This is still a depletion region, but on the P side. And then if you keep on going, the Fermi level is closer to the valence band. So you are inside the P-type quasi-neutral region. Now, just by having this junction, you have created a built-in potential in the device. So there is a barrier now in the device. Okay. This built-in potential is essentially equal to the difference of Fermi levels you started with, because the charge transfer kept on happening till the Fermi level equilibrated. Okay, this is what I was all mentioning. So this transfer happens. This is the slab charges that get generated. You integrate it once, you will get a linearly varying fields. Okay, this is how the field is inside the PN junction with peak field at the metallurgical junction. You integrate it one more time, get the potential and multiply with minus E, and you get your band diagrams, okay, with this potential. Okay. Now, what happens when you apply bias to this structure? Now, this is the equilibrium condition. If you apply a forward bias to this structure, what does forward bias mean? You have two contacts. You have one contact to N-type, one contact to P-type. If you apply positive potential to P-type, negative potential to N-type, then that is the forward bias. So you can think about it. Okay, so there is some noise. So essentially, what happens when you apply a positive voltage on this side gets lowered and this side gets up. So essentially, you reduce the barrier. On the other hand, when you apply a reverse bias across it, you pull down this side and you push up this side. So this difference of the two Fermi levels now is the applied bias. So essentially, by applying the bias, you are tuning this barrier height, or you are tuning the barrier. Okay, consider this almost like you are going on a road and then there is this barrage, okay, which can stop the road at any time and it can come down and it can allow the traffic to pass. So it's almost like that. So there are a lot of electrons in the conduction band. When you make the barrier smaller, you make their transport easier. Similarly for holes, when you make their barrier smaller, holes can easily get transported and you have very large current. On the other hand, in the reverse bias, when you make the barrier very large, you have a lot of electrons here, but then the barrier is so large, they cannot cross it, okay? Because the electrons are distributed in energy. There are not many electrons at these higher energies. So you have very less current. And that is why the rectifying characteristics of a PN junction comes about. You can actually get the basic shape of the IV characteristics very quickly from this picture. So essentially, this is the equilibrium figure, band diagram. Now, remember, this is Fermi level. So you know how the Fermi-Dirac distribution is and how the density of states in the conduction band is. So you know how many carriers are present as a function of energy in the conduction band. Now, there are many carriers in the lower part of the conduction band and exponentially decreasing as you go higher in energy. Now, for these lower parts, all these electrons actually see a big barrier. Guys, keep yourself. So I am again getting. Achha. So yeah, try to keep yourself muted unless, of course, you have a question. Yeah. All right. So, okay. So essentially, now you have few electrons at these higher energies, which have enough energy, more than this barrier height. They will contribute a flux in this direction, or a current, if you want to say. On the other hand, if you look on the P side, there are very few electrons. Okay, Fermi level is here. So there will be very few electrons in the conduction band, but they don't see any barrier. So these few electrons will be very easily able to get injected to this side. Under equilibrium, these two fluxes cancel each other so that there is no net current in the device. When you apply the forward bias, we reduce this barrier. Because of that, now you know the number of carriers are distributed as a Boltzmann distribution. So there are exponentially larger number of carriers now that have enough energy to go over the barrier. So the flux or the current from this side to this side, or electron injection from this side to this side, exponentially increases. While this side, nothing changes. You have similar number of electrons which can easily come back. So you get an exponentially increasing current in this direction. On the other hand, when you apply a reverse bias, the injection from this side to this side exponentially decreases. So you can write down the current something of the form I equals to I naught e to the power QV by KT minus 1, which is the form of the diode equation. Now, what is I naught? To answer that question, one has to properly, but the shape of the IV characteristics you can get from these arguments. So one more important point in this. So this is something which you will see again and again in semiconductor devices. So essentially, transport can happen in two ways. One is over the barrier. Okay, this is called as thermionic. There is a barrier and electrons are going over the barrier. Then there is something known as a tunneling transport. Okay, that comes from quantum mechanics per se. Like in this case, if there were heavy doping on two sides, okay, you make what's called as a Zener diode. In that case, when you apply a reverse bias, what can happen is you can have direct tunneling of electrons from conduction band to valence band or valence band to conduction band. So these are two. So most of the devices we work with actually work on this thermionic principle in which electrons go over the barriers. And all these devices, be it MOSFETs, BJT, Schottky diodes, PN junctions, they all operate on this principle. They have a fundamental energy limit, which you might have heard of. It's known as Boltzmann-Tirani or Boltzmann limit. Now, what is that? Essentially, if you want to increase the current by 10 times, how much voltage you need to apply to the device? So you can do a very quick calculation. Okay. Suppose when you apply V1 voltage, I1 is the current. I apply an extra delta V voltage and current becomes 10 times. So I can solve this and find out that at room temperature, this delta V comes out to be 60 millivolt. So you will often hear this, that you need 60 millivolt per decade of current change. And this is actually a fundamental energy limit of all devices that operate on the basis of thermionic emission or over the barrier injection, because essentially charge times potential is the energy of the electron. And this is currently the most important topic in semiconductor, especially logic scaling semiconductor research, that how do we make devices switch at steeper than 60 millivolt per decade. So there are a lot of approaches by integrating ferroelectrics in the gate stacks, what's known as the negative capacitance FETs, by integrating phase change materials in the source or drain of the FET. These are called phase transition FETs. There are impact ionization FETs. So there are tunnel FETs. So there are many, many approaches for that. And it's a very, very important topic. Okay. So similarly, if we keep on looking at more band diagrams, suppose you're making an NPN structure, which can be either a BJT or say a NMOS. Essentially, you have these three parts in the device, you bring them together, you get a uniform Fermi level, and you will get a potential profile or actually a conduction band profile, which looks something like this. Now, in a BJT or in a MOS, you have three terminals. Okay, either emitter, base, collector, or you have a source, gate, and drain. With VGS or VBE, you control this barrier height. So when you switch it on, you apply VBE or you apply VGS greater than V threshold, this barrier becomes smaller and you can inject carriers from the source or from the emitter into the channel. And when you make this barrier high, of course, the injection stops. So these are the on and off states of the device. Okay, now let me quickly talk about heterostructures, because this is a very, very important aspect of designing the conduction band profiles in your device or the energy landscapes. Because with doping, you can do only so much. Okay, you can either make barriers like these. But if you want to abruptly change the barriers and make them of very interesting shapes, you have to use different materials. So essentially, so this is kind of band lineup of a wide variety of materials. Now, if you make a heterojunction or a junction of these two materials, conduction band changes abruptly. So my electron will see this conduction band change and will see this barrier height. So we can automatically include these abrupt barriers without invoking doping changes. Just by material changes, we can do that. Of course, there are technological issues. When you try to grow two materials on top of each other, they might not have same crystal structure. Sometimes if they have the same crystal structure, for example, silicon and germanium, they might not have the same lattice constant. So when you try to grow one on top of other, many defects can get generated at the interface, which can kill your device properties. So one has to grow in a very careful way using epitaxial growth techniques such as molecular beam epitaxy, CVD, sputtering, all those kind of things. And once you do this, actually you can make all these quasi different dimensional materials such as quantum wells on which all our light emitting diodes, the LED bulbs we are using, they are all based on quantum wells of nitrides right now. Nanowires, quantum dots, all of these can be made using heterostructures. So how do we make a band diagram for a heterostructure? So suppose you have two materials, two semiconductors, whose all the details you know, what are the doping, so you know its electron affinity, band gap, and the Fermi level. Similarly for other material. Again, same deal, when you make a heterojunction, the end thing at equilibrium is Fermi level has to be flat. In this case, electrons will go from here to here because the Fermi level here is higher. So this side will get depleted, this side will get accumulated. So what will happen? The conduction band here, because of the positive slab charge, will change parabolically. Here, it will not be parabolically variation. Actually, it will be a little bit accumulation. It's more like a sheet charge, and you get a structure like this. This is the structure that is behind what's known as a modulation doped FET or a high electron mobility transistor. Now, these abrupt changes in conduction energy are what have led to what is known as a quasi-electric field. So this was a kind of a major contribution because of which Professor Herb Kromer was given the Nobel Prize. So you know that if you have a semiconductor, normal semiconductor, you apply a field across it, the bands will bend. Okay, potential will drop across the device, so the bands will bend. And the slope of the band is the field. So if you have electron, it will go this way, hole will go this way. Now, if you have materials which have a band gap that is changing with position, suppose instead of growing this abrupt heterostructure, we can grow the graded structure. By graded, what do I mean? I add this material 10%, 20%, 30%, then 100%, something like that. So I slowly change the band gap, something like here. So the band gap actually changes slowly. Now in this case, I can have what are called as quasi-electric fields because I'm creating slope in the bands without applying any field. So essentially I can create forces such as I have electrons and holes in my device, but electrons don't see any force, holes see a force. I can even make structures like these in which electrons and holes move in the same direction, which you cannot do with a traditional electric field. Okay, so one actually can tune the electron and hole flow in the device in very, very interesting ways and can get devices with much higher performance if one uses this. So this is a very interesting Nobel lecture by Professor Herb Kromer. So I'll highly recommend. It's written at a very introductory level. And if you read this, you will get a very good idea about this field of how to use quasi-electric fields for device design. So this is also a very active area of research. Okay, so again, before we move on to transport, let me stop. If you have any questions, we can take them now.
Hello, sir.
Yeah.
In PN junction, conduction band energy level always it is higher than the inside. You told that is a smiley shape. Is it true always?
No, so that depends on where your Fermi level is to start with. For example, here, if you dope this N side very heavily, N plus, then this Fermi level will be in there, inside the conduction band. In that case, when you equilibrate, the Fermi level in equilibrium has to be flat. In that case, this conduction band can be below and can be equal to this valence band or even below it. That is what happens in what's called as Isaki diodes, so PN junctions, which are P plus N plus junctions.
So this is valid for when doping is higher in N side.
See, what I have shown is for non-degenerate doping on N side and P side. If you dope heavily, what will happen if you dope heavily? This Fermi level will go closer to the conduction band, right?
Yes, sir.
If you keep on doping heavily, this Fermi level will go inside the conduction, above the conduction band minimum.
Yeah.
Similarly, if you dope heavily on the P side, this valence band Fermi level will keep on going inside the valence band. Now, when the charge transfer happens, ultimately at equilibrium, this Fermi level has to be flat. So what will happen? This Fermi level will be inside the conduction band. So this conduction band has to be below.
I am actually asking about conduction band energy level, EC for both the side, P sides and N side. PC for P side, it is situated higher level.
Oh, right. That is true.
That's why I'm asking.
Yes, it is situated above. Yes, that's true.
It is always true.
It is always true. So what will happen? So one very interesting thing happens. So suppose you do a TCAT simulation on a real device. So what will happen? So let me come to this case. So suppose you apply this. So reverse bias, of course, it will always remain high. There is no question. Now suppose you apply a forward bias. Now this side is coming down. So suppose I keep, as you might ask, I can bring this down, right? Maybe that is what you want to ask. So
no, in this case, it depends upon the biasing.
Right.
All the three diagrams, first one is for zero biasing and the second forward biasing, third one for reverse biasing. All the cases is situated above for P side.
Right.
That's that is the question.
Yes, it is. Yeah. So only case I'm kind of going beyond it. So that what you are saying is always above.
Okay. Thank you, sir.
Yeah. So, but one interesting thing you might see in real devices or when you do TCAT simulation is, see, you keep on applying the forward bias. Now, you know, if you have two resistances in series, one resistance is high, one is small. You apply a bias, most of the bias drops across the higher resistance. So under normal conditions, there are actually, this device has more resistances. So there is one resistance here which controls the current, which is this barrier. Then there are quasi-neutral regions on the two sides which have a resistance associated with them. Normally, either reverse bias or under small forward bias, this junction is what controls the current. So under all these cases, this is how things change and the current would change exponentially, okay, when you apply forward bias. But if you keep on applying forward bias, the barrier becomes very small. Now, this thing does not control the current because this barrier is so small, carriers can easily flow across it. At such high forward biases, the current starts being limited by the series resistances, which is a parasitic resistance. In that case, you will start seeing slopes in these quasi-neutral regions if you do a TCAT simulation. Okay? So that is something you should be aware of.
Sir, actually, there are two reasons, neutral and depletion region. So, the current is flowing in the depletion region actually.
It
Not
is
the
flowing
carriers are
everywhere.
moving.
No, current is flowing everywhere. Current has to be continuous, right?
Okay.
KCL has to be satisfied.
Okay, it is everywhere, neutral
Current
and
is flowing
dependent.
everywhere. Yeah.
Okay.
It depends on what controls the current. See, suppose you have a big water pipe to your house. Then you have a tap.
Yes.
Right? So when you open the tap, water flows throughout the pipe from the tanker.
Yes.
So same deal here. So
Same
water
principle
flows
here.
in the current flows in the full circuit, but this is kind of the tap that controls the current.
Suppose in forward biasing, what are the charge carriers for the current conduction? So both the charge carriers are involved, electrons as well as holes.
Right. So it depends on the position. So for example, if you go deep into the N-type region, there only electrons are present. So electrons will only contribute to current. Similarly, if you go deep into the P-type region, only holes will contribute to the current. Current is same, but then here only holes are carrying, here only electrons are carrying. In the junction, there is injection of electrons from this side to this side, and holes are also getting injected. So in these regions, there is a mixture. Some current, some part of the current is because of electrons and some part is because of holes.
Sir, I can guess one thing in forward biasing. So current will flow from N-side conduction band to the P-side conduction band.
No. See, not current.
Electrons.
Electrons are going from N side to P side. So current will be in the opposite direction.
Yes, sir. Yes. So in reverse biasing case, so electron will flow from conduction band of N side to the valency band of P side. I think.
Actually, no. So see, we are going only over the barrier. Now, see, the electrons in the conduction band from N side now see a huge barrier.
Yes.
So they cannot go to this side. That injection is very small. On the other hand, there are electrons or minority carriers on the P side. And they don't see any barrier. They can come down the barrier. So the reverse leakage current is mostly because of these minority carriers or the generation carriers within the depletion region. So the electrons are going from here to here. So you have a current from here to here.
So only thing is possible if we increase the reverse biasing voltage, so this depletion width will be less.
No, it will keep on increasing, right?
No, depletion width will be increasing.
Right.
Okay.
It will keep on increasing unless you have heavy doping on both sides.
Yes.
So that the carriers can tunnel through this barrier.
Okay. For tunneling, heavy doping is required.
Yeah. You need heavy doping so that the depletion width is small.
Okay, sir. Thank you, sir.
Yeah.
Sir, sir, I have a question.
Yeah.
Sir, what is the effect of quasi-crystalline nature of the material on these band diagrams?
Okay, so that's a very good question. So in transport, I'll deal with it. Actually, that's a more complicated. See, most of the time when we do TCAD simulations or we try to model the devices, we don't consider polycrystalline nature in the band diagrams.
Yeah.
What we say that is the electron transport gets affected. And the reason is, so see, okay, it's a very interesting way to look at it. So suppose, so I was mentioning about these two materials of some property is different. Now, when you have two different grains of the same semiconductor and you have a grain boundary in between, that grain boundary can have charges. And when you make the band diagram across this interface, your conduction band might have a discontinuity because of that grain boundary. And that is why we say that when electron is moving in the conduction band, it might get scattered because of this interface. So mostly we do not show it in the band diagram, but actually the effect in transport happens because of the variation in the conduction band in the band diagram. So I hope it's clear. So we mostly deal with that question in the transport part. We don't do that much in band diagram as far as modeling is concerned.
Okay, even for polycrystalline samples also, we can represent the band diagrams, no?
Yes, yes, you can.
Okay, sir. Okay, sir.
You can. Like for polycrystalline silicon solar cells and all, yeah, we regularly use band diagrams. Some things that do change are, see, polycrystalline material, depending on the grain size, the band gap can change also. Suppose your grain size is very small, then the band gap can increase. So those kind of effects you will have to take into account, that the material has changed slightly. But as long as the grain sizes are much larger than de Broglie wavelength, let's say more than 100 nanometer, then you can keep on using the bulk band structure and make the band diagrams accordingly.
Okay, sir. Okay, sir. Thank you.
Yeah.
Excuse me, sir.
Sir, I have a question, sir.
Yeah.
So actually, I wanted to know that how that carbon nanotube PN junction diode, it is different from this usual PN junction diode.
See, the
how
thing,
is it better than that?
Go ahead. Yeah. So,
Yes.
Yeah. So see, the thing that gets changed is because you are starting with a different material, carbon nanotube. So the starting band structure is different. So carbon nanotubes are of many different kinds. So there are, I think, semiconducting and metallic carbon nanotubes. So depending on the carbon nanotube you are starting with, you need to know the band structure of that carbon nanotube. Then you dope it. So once you know the band structure, you know the density of states. So based on that and the doping, you can find out how many carriers you have in that material. And then following the same process like we have been doing, you can make a band diagram of the PN junction. It's just a different material. That's it. No fundamental difference other than that.
So the process of conduction is same in that CNT also, sir? CNT diodes.
So what do you mean by process of conduction? See, if it's a PN junction.
The process mechanism due to which we get current in PN junction diode. Is that mechanism
all
same?
materials same. It's the same thing. All materials are similar in that sense, that they have a band structure where there are allowed states. You fill those states by doping or by field effect, and those electrons contribute to current. So when you change material, the only thing that changes is the band structure.
Okay, sir. Thank you, sir.
Yeah. Any other questions?
Excuse me, sir.
Yeah.
Can you throw light on something in change in the band gap of the semiconductor by doping the metal ions like that? How it happens?
Right. So what happens is when you start doping, but see what you are talking about is not as such doping, but more like alloying. You kind of increase the concentration to 1%, 2%, very high number. So what happens in that case? Let me just take any. Okay, maybe earlier we were looking at this donor. So see, here we have put this impurity atom in the silicon, and that has led to this extra energy state in the band diagram, in the band. Where there was zero density of states, now you have some extra state. Now, as you keep on increasing the density of these impurities, you keep adding these defects here. So ultimately, these defects themselves start to form a band, which is known as an impurity band. And at a very high concentration of these impurities, this impurity band merges with this conduction band. So there is a continuity of density of state. So essentially your band gap shrinks because of that.
Okay.
Yeah.
Then how it is different from multi-layer films when metal is coated on the semiconductor film? Is it work same way or different way, sir?
No. That is different. So see here, you are putting atoms in the material. So you are changing the band structure of the material. While the thing you are mentioning, when you are putting metal on the semiconductor, then we are making a heterojunction. So that is where we were discussing about band diagrams, where one side we have metal, other side we have semiconductor. Right now, we are putting metal atoms inside the semiconductor. So we are changing the band structure of the material itself. Yeah.
Thank you.
Yeah. Any other questions? Okay, I don't see any other questions in the chat also. All right, so let's then move and come to the third part, okay, which is the carrier transport. So we have looked at the how to calculate the mobile carriers concentrations, then how is the energy landscape, and now we come to the third part. So remember, current density is QNV. So now we come to that velocity part. How do we calculate the velocity? So now let me talk about the different transport regimes that are present in solids. So here some of the questions that were coming become very relevant. See, on one extreme, we have materials that are perfect crystals. Okay, they don't have any phonons. These atoms are not moving. So these are perfect crystals in which if the electrons move, they do not scatter. In these cases, the velocity of the electron is given by V equals to 1 by h bar, the gradient of Ek, a slope of the Ek diagrams. This is the ballistic limit of transport. Then most of the semiconductors we deal with, there is a small degree of disorder. For example, I was showing that doping of 10 power 15 per centimeter cube, in which there is 10 atoms in a billion. Okay, very, very dilute impurity has been put. Now, in such a case, electrons mostly moves in a perfect crystal, but once in a while, it encounters this impurity atom and scatters from that. So this is a low level of disorder. And under these cases, we talk about scattering, mobility, velocity field relations. Most of the semiconductor physics is done in this limit. Then there are materials which have a relatively large disorder. So here comes most of the organic semiconductors, polymers, then polycrystalline or amorphous semiconductors, where there is a very large degree of disorder. Now, in this case, there is no well-ordered position of atoms. Under these cases, when we want to calculate the velocity of the electrons, we use these concepts of localized states, band tails, or hopping conduction, in which the electrons get trapped at one position, get released, hop to the other position, then hop to the other position. So they usually have very poor transport. Then there are structures which are very small. So this is where we are approaching in current state of the art devices such as FinFETs, nanosheet FETs, nanowires, a lot of those devices. Under these cases, the size of the devices is becoming comparable to the wavelength of the electron, de Broglie wavelength of the electron. So we have to take into account the wavelength and the reflections that happen. So under these cases, how do we calculate the current? So these are all different regimes we have to worry about. So to deal with all these different cases, there is a whole hierarchy of transport theories. So among semiconductors, probably transport is the richest in terms of physics because there are many, many things that are going on. On one level is what's known as quantum transport, where you use the Schrodinger equation and you take the wave nature of electron into account and calculate the net current that is present. Then, if you neglect the quantum effects, and this is where most of the semiconductor physics gets done, is what's called as a semi-classical transport, where the quantum mechanics is taken into account and band structure is calculated and effective mass is found out. Now, once you know that because of effective mass, my electron is behaving like a free particle, I say from that point onward that I can use mostly classical physics now. Okay, that it's a particle, it does not have a wavelength. So that is the semi-classical transport, where we deal with what's called as a Boltzmann transport equation. And then there is, if you remove the hot electron effects, hot electrons are which have energy much higher than given by the Fermi-Dirac distribution. So much higher of the thermal energy of the electrons. Under these cases, we can treat the flow almost like as hydrodynamic or a fluid flow. This is where drift diffusion equations come, which I think we use most often. Then there are two different approaches to these transport hierarchies. One is a single particle approach, where we say, I'll do calculations for one electron and multiply with the density, and I'll get all things correct. Okay. So this is where Monte Carlo simulations come, where you take an electron and you follow its trajectory through the device. And then you do it for many, many single particles. And from that average, you get the net device behavior. Then on the other hand, are these collective behaviors, where we work with either electron density. Okay, we are working with number of electrons per unit volume, like in drift diffusion equation. Or there is Boltzmann transport equation, where we work with the distribution function, how it changes. And similarly, there are quantum kinetic equations. So this is quite involved. So of course, we do not have time to go through all of them. I'll go through 2 or 3 topics very quickly to give you a flavor of what it is. And then if you are interested, you can dig deeper into it. Yeah. So let's first start with the small degree of disorder, because this is something we are all mostly familiar with, and this is the most general, most often encountered situation. So under this case, the electrons, as they move, as I said, most of the time the electrons can move easily, but then once in a while they encounter these defects and get scattered from that. What are these defects? So they can be, of course, impurities such as the donors or etc. atoms we have put in. They can be grain boundaries, for example, in polycrystalline material. They can be lattice or phonons, because all these atoms are moving around their mean positions. So they can scatter the electrons. And then, like in a MOSFET, at a silicon oxide silicon interface, there is surface roughness that can also lead to scattering. So how do we deal with them? So we find out using what's known as the Fermi-Golden rule. I think tomorrow you will hear about it from Professor Regde. Using Fermi-Golden rule and the potentials for each of the scattering center, you find out the scattering rates, that how quickly the electrons get scattered from a certain density of scatterers. And you can find out these are the scattering rates. Okay, 1 by tau. Tau is the mean scattering time, and 1 by tau is the scattering rate. So you can find out the scattering rate because of all these different scatterers present in your material or in the device. And then you use what's called as a Matheson's rule. You assume that all these scattering events are independent. So the net scattering rate is simply the sum of the scattering rates. So you find out this net scattering rate. Typically, the scattering rate can be of the order of 0.1 picosecond or so, just to keep an order of magnitude in mind. But of course, these things change depending on doping concentrations, temperature, all those things. So now, one way, so suppose you apply a field. So you know, in band diagram, there is a field at each position in the device. So suppose there is a field is 0. Now electron is always moving around. Okay, it's never at rest. Because it's occupying the K position, it has a kinetic energy, so it's always moving around. But in general, its average velocity is 0. because it gets scattered, it goes forward, backward. So net flux is 0 because of the electron. When you apply a field, because of the field, the electron gets a net average velocity, which we call as a drift velocity. Now, this drift velocity is actually proportional to the electric field, and the proportionality factor is known as the mobility. And the mobility, actually one can prove, is given as Q times the mean scattering time divided by the effective mass. So this is the expression I was referring to earlier when that question was raised, that why do holes have lower mobility compared to electrons? And the reason is because the effective masses of holes is usually heavier than electrons. There are no fundamental reasons for that, but then that's how it has come to be in most traditional semiconductors. So this is the drift velocity that you can then use to calculate the current. Now, if you keep on increasing the field and measure this drift velocity, typically the behavior you get is initially this drift velocity increases linearly with the field. Then the increase starts to become slow and then it saturates. The reason behind that is when you go to very high fields, the kinetic energy of electrons is sufficient to start emitting longitudinal optical phonons. So that is another kind of scattering that needs a certain minimum energy of electrons. If the electron energy is less than that, it cannot happen. So as soon as you cross that line, that scattering takes over, which is so fast that no matter if you increase the field, now that velocity does not increase. So an example is, suppose, see, you are earning money and you are spending it also. Now, suppose field is your kind of earning, that increases and your spending is not increasing. So spending is like scattering. So if the earning is increasing and spending is not increasing, then slowly your savings will increase. But suppose at some point your earnings also become equal to your spending, then of course your savings will become constant. Okay, so that is kind of the idea. So the velocity ultimately then saturates. So this is the velocity then one can use to calculate the current, because the current is QNV. Typical order of magnitude of the saturation velocity is about 10⁻⁷ centimeters per second or so. Okay, now what about this mobility? Now this mobility is, remember, it has this scattering time. So it has a lot of physics involved in it. Okay, Hall effect actually has led to almost, I think, 3 or 4 Nobel Prizes till now, because a lot of physics about how electrons behave inside solids is contained in Hall effect or in the mobility. So essentially, this is from a Hall effect measurement where mobility in silicon has been measured as a function of different doping concentration. And it is measured as a function of temperature. So clearly you can see as temperature increases for very low doping concentration, where there are not many impurities, the mobility decreases with temperature. Why is that? Because as you increase temperature, the electrons start to move heavily. The atoms start to move much more rapidly, or the phonon population increases. So the phonon population is given by the Bose-Einstein distribution. So your phonon population increases. So the electrons get scattered more. So the mean time tau reduces. So the mobility reduces. As you reduce the temperature, less number of phonons. So your mobility rises to very, very large numbers. So see, one way, if you want very high performance out of your device, is of course to cool the device so that you can get very high mobilities. So that is sometimes done in some specific applications. Then if you keep on increasing the doping concentration, you are adding more and more dopants or impurities inside the material. So because of that, what happens? you have this extra scattering because of these impurities coming into picture. So your tau reduces. That's why your mobility comes down. At higher temperatures, the phonon scattering limits. At smaller temperatures or lower temperatures, the ionized impurity scattering dominates the this tau. Okay, because essentially this is a harmonic mean. So the minimum of them essentially controls the tau. So this is, again, as I was saying, it's a very active area of research. People want materials with very high mobility so that they can study transport. Gallium arsenide is kind of a main structure which has generated a lot of Nobel Prizes and a lot of new discoveries like quantum Hall effect, fractional quantum Hall effect. And the reason behind that was development in technology, especially molecular beam epitaxy, in which they did a lot of technological improvement in the sources of impurity, removing them, and they could get mobility. So this is from 2007 at low temperatures, so around 1 Kelvin or so, they could get mobility as high as 36 million centimeters square per volt sec at low temperatures. Okay, it's a huge number. You can find out the mean free path, or the between successive scattering events, how much path the electron travels without scattering is of the order of 100 microns. So essentially, you can look at the quantum nature of electron without scattering under these cases. Okay. So essentially, as I was saying, once you know this drift velocity, what is the drift current? It is Q and V, okay, where V is mu times E. Similarly, there is a diffusion current also. Suppose there is a carrier concentration gradient. For example, in a PN junction, when you forward bias it, you have a lot of electrons on one side and less electrons on other side. So there is a diffusion current because of that. Just like you put a drop of ink in water, you do not mix it or do anything, and automatically in some time it will spread through the water and make it colored. That is because of diffusion. So for that, we use what's called as Fick's laws, that the flux of the carriers is proportional to the gradient of the carrier concentration, and the proportionality constant is known as the diffusion constant. So essentially, so the current is, for current, getting current, you multiply with the amount of charge that is there, and this is the full current expression. Essentially, if this is the carrier concentration, electrons will diffuse from high to low concentration. So the current will be in the opposite direction. Okay. So in this case, dN by dx is negative. That's why the current is in the negative x direction. So this you can use to remember the signs on this. Similarly, you can write the diffusion current for holes. Now, the diffusion coefficient actually has all the same physics as mobility. It is decided by the scattering events inside the material. So there is a relation that relates the two, which is known as Einstein relation, that d by mu is a constant, kBt by q. So if you know one, say from Hall measurement, you can find d. Once you know all this, essentially you can find the total current, which is the drift plus diffusion, both terms together. Okay. So this is one aspect of doing devices or calculations when you have some amount of scattering present in the material. So this is what is known as a drift diffusion transport. Now let me just introduce you to some of the higher level theories that are present here. Now the drift diffusion transport is limited to what's known as a relaxation time approximation when you can define mobility or diffusion coefficient. Now, as devices have become smaller, you encounter less and less scattering events. And when you have few scattering events, it's difficult to define average scattering time, right? For calculating averages, you need a large data size, lot of scattering events. So under such cases, it becomes difficult to define a mobility or diffusion coefficient. So under these cases, one can work with either the Boltzmann equation or the Monte Carlo simulations. Now, in Boltzmann, this is what's the Boltzmann transport equation is. F is the occupation function. If you remember, under equilibrium, the distribution or the occupation function is the Fermi-Dirac distribution function. When you apply field in a device, or you have a gradient of concentration, then this distribution function can change from Fermi-Dirac. So Fermi-Dirac is valid only at equilibrium. Whenever you are applying bias on a device, you are shining light on it, you are going out of equilibrium. Because of that, the occupation function changes. So the Boltzmann transport equation is the differential equation of this occupation function, and it changes because of either scattering, because of field, or because of diffusion. Okay, and this is the form of the Boltzmann transport equation. There are no general solutions for. We know that this has all the physics in it, but there are no general solutions for it. We can solve it under some approximations. Now, to solve this, essentially del F by del T scattering term is there, which has this transfer Sk prime K, which tells us the scattering rates from K prime to K. This is something I think you will look at tomorrow when you deal with Fermi golden rule. So this is what is calculated using Fermi golden rule. So essentially you come to know of this term from this. And then this del F by del T, many times we do what's called as a relaxation time approximation. We say that I am disturbing the system out of equilibrium very little bit, not by a whole lot. So my F, the new distribution function, is slightly different from F naught. F minus, so we replace del F by del T with F minus F naught by tau. And then under steady state, you can get some expression like this, that under non-equilibrium, your new distribution function is equilibrium plus some small part, extra part, which includes the field, the velocities, and the scattering. Okay. So if you are interested a little bit more into this, you can look at some of the transport books, such as one by Professor Mark Lundstrom from Purdue. I think fundamentals of transport, something like that. Similarly, there are Monte Carlo simulations in which, for suppose you have a very short device where there are not sufficient scattering events. So what is shown here is the band diagram under bias of a MOSFET. In this case, 30 nanometer dual gate MOSFET. This is a very old paper actually, okay, from 92 or so, from IBM. So this is how the conduction band varies. This is the source, this is the drain, it's an NMOS. So this is heavily doped, this is heavily doped. So you can see these dots are electrons, many carriers. These drain also has a lot of electrons. This is the barrier which you control with VGS. So essentially, there are very few, these electrons have enough energy to go above the barrier, so they get injected. Then they get encountered scattering events, so they lose the energy, come down, and then ultimately they reach the drain. So what is done in Monte Carlo methods is you take one electron, you know what the field is like in the device. So you follow, you know what's the velocity of the electron, you keep on following that. Then you have the scattering events present in the device. So you randomly choose from them. Okay, that's what Monte Carlo words come from. It's like gambling, probability, that you choose from them and scatter the electron. And you keep following the trajectory. And then you do it for a lot of electrons. And then you start seeing how the electron transport happens in the device. For example, here you can see that electrons actually, average electrons, have much higher kinetic energy than the minima of the conduction band. Okay, they have much higher energy. That's why their average velocity goes much higher than the. So all these kind of insights one can get from these kind of calculations. So actually, it's already 6. I'll just quickly wrap up. by giving you few examples of this very small structures. So as I was mentioning, whenever the size of the device starts becoming comparable to the de Broglie wavelength of the electron, multiple things happen. One thing is, of course, the density of states changes, the band structure starts to change. The other thing is, in transport, we have to worry about reflections from the interface. For example, how do we deal in such cases? So suppose you have a conduction band profile which is like this. Okay, this is very easy to make using epitaxial techniques. Now, as electrons come to this interface, one is, of course, they can go over the barrier, and other is tunneling through the barrier. How do we do calculations for those? So we can use what's known as a transfer matrix approach. Essentially, you take the Schrodinger equation, you solve them in the three regions, you will get traveling wave solutions outside the region, and within the barrier, you will get decaying solutions. You might have looked at that maybe in earlier lectures or in your quantum mechanics courses. And then you tie out these wave functions by applying the boundary conditions at these two boundaries. Essentially, that the wave function is continuous and its first derivative is continuous. Once you do that, essentially the picture you get, you have an incident wave of electrons and some reflection. Similarly, some transmission and some incidence from this side. Once you have all this, you can write down, just like we write Z port parameters, S parameters in electrical engineering, you can write down a matrix which tells us that how much part of incidence gets reflected and how much gets transmitted. So the part that gets transmitted is known as the transmittance. Here, transmittance is plotted T of E as a function of electron energy. So classically, you know that if I have an electron whose energy is less than the barrier height, it cannot go through. Okay, classically, we know that's the way it is. So the transmission function for a classical calculation is this dotted line. That for energies less than the barrier height, say the barrier height is 0.5 eV, the transmission is 0. If the electron energy is more than 0.5 eV, the transmission is 1. But when you include the quantum effects and the fact that the electron has a wave nature, you have to consider interferences because of multiple reflections that happen. And what you get is this solid line, essentially this transmission. So you can see for very high energies, the quantum result and the classical result match. But for energies comparable to the barrier height, they change quite differently. Even for electron energy larger than the barrier height, there can be a very high probability of reflection. Okay, it can still reflect strongly. And these are important effects in devices such as heterojunction bipolar transistors and some other cases. So this is known as transmission. Once you know the transmission, you can calculate the current as such, in which you have injection of carriers. You have certain Fermi level on this side, certain Fermi level on that side. So you inject carriers from this with certain transmission. You inject carriers from this side with certain transmission. And the net injection is what gives you the current. A very interesting example of a device is what's known as a resonant tunneling diode, in which there are two barriers present like this. One can again easily make this using epitaxial techniques. People have made them in gallium arsenide, in gallium nitride, and got very interesting IV characteristics. So how do we calculate the transmission in this case? Actually, if you are interested in the full calculation, you can look at Davies' book, John H. Davies. The book is The Physics of Low Dimensional Semiconductors, which talks in great detail about this transfer matrix method. So essentially, if you look at the transmission through this full structure, what you get is these resonant transmissions, that even though the electron energy is less than the barrier height, you can get 100% transmission of electrons. Okay, this is almost like magic, that even though there are big barriers in front of you, you can transfer through the walls. because this is all comes from quantum mechanics and has been experimentally confirmed in many, many cases. So because of this behavior, how does the IV characteristics of a RTD look like? When you apply bias, initially, so see, there are a lot of electrons, so both sides are usually heavily doped. So a lot of electrons. Now in this quantum well, there are discrete states there. So whenever the electrons on the one side get aligned with these allowed energy level in the quantum well, you have a resonant transmission. So initially, as you increase this side, more and more electrons can tunnel through that. So your current increases. But at some point, you keep on applying bias, the conduction band minima goes above this allowed energy level. So there are no electrons now to tunnel. So the current decreases. So you get a negative differential resistance, which is used very heavily in high frequency devices like oscillators at like very, very high frequencies, tens of gigahertz or so. And another very popular application for this kind of a calculation, as I was earlier saying, in current state of the art FETs, one of the limitations we are facing is the 60 millivolt per decade limit. Because typically in a MOSFET, we are injecting across this barrier. And because of that, we have to apply at least 60 millivolt to increase the current by 1 order. And because of that, we cannot scale the VDD of our ICs. So another approach which people have proposed is what's known as a tunneling FET, in which the electrons don't go over the barrier, but directly tunnel from the valence band into the conduction band, and we can switch on and off by changing the barrier width. All right, so this is all about transport. Let me then wrap up. So in a device analysis, then one more thing is needed is we have to keep track of the carrier concentration changes that happen because of the current flow. See, in a given region, we are injecting. So we had carriers because of doping, but then we have carrying the current. Because of that, the carriers keep on coming out, in and out of any region. So the carrier concentration at any point can change because of that. So to take into account, we use what's known as continuity equation that takes into account the current as well as the carrier concentration changes because of generation recombination mechanisms, such as you already know, if you shine light, you are generating, there is impact ionization, or mechanisms like band-to-band recombination, Auger recombination, Shockley-Reed-Hall recombination. So because of all that, you can have generation or recombination. So once you have all that, then this is the full picture. These are the fundamental equations, essentially Poisson equation, which is always valid. Along with this, there is Schrodinger equation whenever the quantum effects are important. There are continuity equations to keep count of electron and hole concentration in the device. These are always valid. Then depending on the transport regime, if it's drift diffusion, then these are the equations you work with. If you are in the ballistic regime or you are using transfer matrix method, you are using Boltzmann equation, you are using Monte Carlo method, then you will calculate the J in a slightly different way. Once you have all that, then essentially you can get to the current voltage characteristics. And of course, you can go backwards. Suppose for your application, you need a certain current voltage characteristics. You can go backwards and design the device. So that's it from my side. So thank you. And if you have any questions, we can take them now.
So Amit, thanks a lot. That was a very beautiful presentation and you were talking for more than 2 hours. So thank you very much.
Thanks.
Any question from the audience?
Yes, sir. Sir, I have a question. That about mobility, although we explain on the basis of the effective mass, right, sir? But as we know that holes are nothing, rather they are vacancy.
Right.
Just a vacant space. So
Right.
how we can assign mass to them, sir?
So see, it's more like an effective mass. The reason is, okay, so let me give you an example. So see, we play this game of musical chairs in which there is one empty chair.
Yeah.
Right, or one extra person, whatever.
Yeah.
So now, as it happens, you can do the calculations in valence band with the filled electrons also. It's just that the number of filled electrons in the valence band is of the order of Avogadro number, while the empty states are much smaller in number. So it becomes easier to kind of work with that empty state. So like in the case of musical chairs, randomly it will look like that empty chair is moving around. Even though that chair is not moving, people are moving. Right?
Right. Yes, sir.
So it's kind of an idea in that sense. So the effective mass there comes from the curvature of the band because the carrier still behaves. So let me go to the band structure again. Yeah, so see, this EK, you fit a parabola to it. That EK is how an electron behaves in a solid.
Yeah.
So that empty state behaves like a EK of this curvature, which has a certain effective mass.
Okay.
Any other questions? Okay, if not, Rick, looks like this is it.